Hey guys, sorry, my video just cut off a minute ago, so I got to do a second little section here. I was just talking about Green's theorem. In the case of a vector field that only has an m and an n component, the curl of that vector field is really just n sub x minus m sub y. In other words, Green's theorem right here is really just the two-dimensional version. It's just the two-dimensional version of Stokes theorem. So when we have a curve in space and we have a surface that's not just a flat region in the xy plane, but some surface that's in three-dimensional space, then we can use the sort of the beefed up version of Green's theorem in order to do the line integral and relate it to a surface integral. And that beefed up version of Green's theorem is called Stokes theorem. Okay. Now you remember that with Green's theorem, we had to orient ourselves in such a way that we were going around the curve with the region on our left side, counterclockwise, in other words. The same sort of thing is kind of true here as well. When I talk about compatible orientation, when you have a curve, there's of course two ways to orient it, right? And with a surface that's not closed, there are two sides to that surface that could be chosen as the positive orientation. They need to be compatible. Now, what do I mean by that? If you take this trash bag, if you take this surface S, and imagine that you were able to like squish it down, right? If you squished it down so that it was right between the curve C, it was just sitting right between the curve C, you would need the positive orientation of the surface to be kind of compatible with the way the curve is turning. So again, essentially, you can use this sort of right-hand rule idea to figure it out. If you curl your fingers in the direction of the curve, your thumb is going to point in the direction of the surface that's supposed to be the positive orientation. In this case, it would be upward, right? The upward direction. So now, in some places, it may look like it's downward. If the surface is really, convoluted like this, there's going to be the ds vectors here, right? These perpendicular vectors, they're pointing in all sorts of different directions. So, but if you imagine attaching those vectors there, and then you push down the surface, you push this trash bag back down so that it lays right between the boundary of that curve, right? All of those normal vectors are going to be pointing straight up, right? Which is consistent with the direction of that curve right there. Okay, so let's do an example, okay, of Stokes theorem. Well, maybe before I do that, let me give you another little piece of extra credit. So I told you about my cat earlier. I also have a brother, and my brother lives in Wisconsin, and what he does for a living, this is the thing I want you to write down for number 3, he plays the French horn. He's a professional musician. So just write French horn. That is your third item of extra credit for the upcoming test. All right. Awesome. Okay, let's do an example at this point. So let's do this. Example of Stokes theorem. Evaluate the line integral of f dot dr, okay, where the f, the vector field, is xy, comma, yz, comma, xz, okay, and C is the triangle with vertices. So the vertices are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? Let me draw that so we can have a little picture to look at here. So again, the three-dimensional picture. We don't have to draw this vector field at all, but I should draw at least what the curve is here. So it's just this triangle right here. And it's going through each of the coordinate axes at the point 1. Okay, so we're going to use this triangle. I want to make one other comment. I should have. This needs to be also expressed in the question. Viewed counterclockwise from above. So it's a closed curve, right? But we can calculate the line integral of that closed curve in whatever direction that we want. I know that I've said before that counterclockwise is, viewed as being the positive orientation, but we could have asked for it in the negative orientation as well. But if we did that, then we would be, putting a minus sign into our calculation. Well, I'll explain it a little bit better, I think, once I actually talk about the surface as well. So the counterclockwise direction would be like this, okay? So if you go up onto the plus z axis and you stare down at this picture, right, this would be the direction of the arrows. So how do I know that I want to use Stokes Theorem here? Well, I'm being asked to calculate a line integral around a closed curve. That closed curve is not in the xy plane, so we're not talking about Green's theorem right now. But I also notice that because the curve consists of 3 different sections, to actually brute force do the line integration is going to take a while, because we're going to have to parameterize all 3 portions of this curve, right? Might be easier to just replace this line integral with a surface integral, where the surface that we're going to use is going to be just the plane that is sitting between the sides of the triangle. It's just this plane right here. It's a part of that plane, okay? And my right-hand rule, if I kind of curl my fingers in the direction of the curve C, my thumb is telling me that my ds vector, the compatible orientation for the surface, is going to be that the ds vector should be pointing roughly upwards, right? So we're going to want to keep that in mind. We're going to be parameterizing the surface, okay? And we're going to orient the surface upward. Okay. So let's see if we can do that. We have a few things to do. We have to find the curl. We have to figure out what the surface is. Well, the surface is just a plane, right? So the equation of this plane, I think it's pretty quick for you guys to figure out that the equation of the plane is just x plus y plus z equals 1. Okay? Plane goes through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, if I give you 3 points, right, you can always find the equation of a plane. That's something to review for the final. It goes back to chapter 11. Okay? So anyway, this is the equation of the plane, and I can parameterize it as a function. So I can let x equals u, y equals v, and z equals 1 minus u minus v. Okay? Let's try and calculate our ds vector. Okay? So the ds vector in my Stokes theorem here is really just r sub u cross r sub v. Okay, so actually, let's just calculate r sub u cross r sub v, right? This is really the thing that we need to do right now. I, j, k. And then r sub u is just 1, 0, and negative 1. And r sub v is 0 and 1 and negative 1. If you work out that cross product, you're going to get 1, 1, and 1. Okay? You're just going to get 1, 1, and 1 out of that thing. And notice that the k component of that vector is positive. That means that the ds vector is pointing upward. That is the correct orientation. This surface is oriented. See, they never told you which way to orient the surface when you're doing this flux integral. It's not told to you. You have to know that it has to be chosen in a compatible fashion with the orientation of the curve. We did give you the orientation of the curve C. That will then force us to orient the surface in a compatible way that obeys that right-hand rule. This is what Stokes Theorem requires. Okay? Great. So we have our ds vector now. Okay? Oh, and just so we know the parameter domain here. So x and y are the same as u and v. If we just look here in the xy plane, right? We just have this triangle right here. Goes through 1 and 1. We're going to need that when we set up our integration. Okay, so let me just save my notes here. So the ds vector is 1, 1, 1 dA. All right? Now, I also have to find the curl of f, right? I have to take the curl of the vector field. So here's the vector field right here. Let's talk about the curl of it, or let's calculate the curl of the vector field. So this is where we once again make a matrix, I, j, and k. This time we put our partial derivative operators on the second row for the curl, and then we just put our components of f into the third row. Okay, so for the I component of this, we're going to get nothing here, minus y right there. Okay. The j component is going to give me nothing right here, but then minus z right there. And then the k component is going to give me nothing right here, but negative x right there. Okay? All right, and so that is the cross product. That's the curl. So if I now imagine, I'm going to go ahead and erase this part. Sorry, I don't have much room on this board. If I imagine setting this up, right? I've got my u and my v that I'll figure out from this triangle in just a second. The curl of f is right here. Now, remember, let me just rewrite it. I have to write everything in terms of u and v because I've parameterized the surface. So negative y is really negative v. And negative z is really u plus v minus 1. And negative x is just negative u. I have to take that and dot it with 1, 1, 1. Which really just means I'm going to add all of that stuff up. If you add all of this stuff up, right, negative v plus u plus v minus 1 minus u, you get negative 1. You get negative 1, right? Okay, there you go. You get negative 1 out of that. So actually, we don't have to do the double integral at all. Because remember, you can take the minus 1 out. Now you're just double integrating dA. That's simply the area of this triangle. And that's going to be 1/2 of the base times the height. Okay? So my final answer is going to be 1/2. Okay? Negative 1/2. That is the final answer to the problem. Okay? Well, that's pretty slick. Okay? Hopefully this makes sense. Of course, if you have questions, you should feel free to write them down and get a hold of me, and I'll be happy to try to answer them. Okay. All right. So I told you about my brother. I told you about my cat. Let me tell you about my my niece. I have one niece because my brother had a child 4 years ago. So I have a 4-year-old niece. So for item number 4, I want you to write down her name. My niece's name is Caitlin. And one day I hope to be taking her climbing lots of mountains, and maybe, who knows, maybe I'll be teaching her Stokes Theorem one day. Yeah, it's always a possibility. Okay, anyhow, so here is the statement of Stokes Theorem. Now, you notice that Stokes Theorem, there's two sides to the equation. We can take the line integral and turn it into a surface integral. But we can also go the other way around, can't we? Maybe we have a surface integral of something, and if the thing that we're integrating happens to be the curl of a vector field, we could actually trade in the surface integral for a line integral instead. You see, the two things are equal. It's just that they may not be equally difficult to calculate. On the last problem that we did, the line integral would have been pretty hard because the triangle had 3 curves to it. It would have taken a while to parameterize all of those curves to come up with the answer. Whereas the surface integral turned out to be quite simple. Okay? But this can also work the other way around. It can be also possible to use it the other way around. So let me give you an example of that. Oh, but I also want to tell you another extra credit item. Okay? So for the 5th thing, My dad, I'm going to tell you what my dad does. My dad is still working, and my dad is a physician. So please write the word physician down on your homework assignment. Okay, so you've had 5 different extra credit opportunities already. Each one of them is a half of a point of extra credit on the final exam. Okay, let's do this example. Evaluate the surface integral of the curl of f dot ds. If you see something like that on the test, you know that this is a Stokes Theorem problem because it's already set up in the format of the right-hand side of Stokes Theorem. Okay, so where S is the part of x squared plus y squared plus z squared equals 5, okay, above z equals 1. So this is a sphere of radius square root of 5. We're looking at the part of the surface above z equals 1, oriented downward. I'm going to throw a little twist in here. Oriented downward. And I also have to tell you what the vector field is. The vector field is x squared yz, comma yz squared, comma z cubed e to the xy. Not a particularly nice vector field. Okay? It's not a particularly nice vector field. Of course, we're not asked to find the surface integral of f, right? We're being asked to find the surface integral of the curl of f, okay? But the okay, so I could tell you what the curl of f is. We actually don't need to calculate the curl of f, even though we're being asked to evaluate that. And that's because instead of doing the surface integral, what we're going to do right now, guys, is instead do the line integral. And for the line integral, I just need the vector field f. I don't need the curl of f. If you were curious, you could calculate the curl here. It's not a pretty expression at all. It's going to be a function that would be messy to find the surface integral of. So I'll just write it down here for you so you can look at it, but we're not going to do anything with this. We're not actually going to calculate the surface integral of this, okay? If there was no Stokes Theorem, we would be stuck right now doing the surface integral of this, okay? But instead, I'm going to go ahead and erase it because we don't need it. Instead, we're going to do the line integral of the boundary curve. So C has to be the curve that forms the boundary of S. Let's take a look at a picture here. The picture is going to help us understand the problem here. Okay, we have a sphere of radius square root of 5. Okay, but we're only looking at the part of the sphere that is above z equals 1. So there's z equals 1 right there. I'm going to get rid of the rest of the sphere here. So we're just looking only at the part of the sphere that's above here, and we're orienting it downward. So that means that my ds vectors are going to go down, like that. Okay, so downward orientation. And it's not a closed surface. We're not including the disk that is kind of at the base here. But that disk is, of course, it is, of course, forming the curve C that is the boundary of the region. Now, be careful, guys. We have oriented the surface downward. So whichever direction I traverse the curve C, the ds vectors, if I push the surface down in between the curve, has to point downward. That's going to require that I actually traverse the curve clockwise. Okay? What is that curve, by the way? Well, if I put in z equals 1 right here into the sphere, I see that x squared plus y squared is equal to 4. Okay? So what I need to do to calculate the line integral is I need to parameterize that curve. Okay? And of course, z is equal to 1. That was kind of clear. It's a circle of radius 2. Normally, if you're going to parameterize a circle of radius 2, this is how you would do it. Okay? But that is the normal clockwise rotation. okay? So you have two choices right now. You can either go ahead and leave the parameterization like this. By the way, t is going all the way from 0 to 2 pi. You can either parameterize the curve this way, or, and then, well, if you do it this way, then when you get the final answer for the line integral, you'll have to throw a minus sign into your answer, right? So you can do that, or we can just change the orientation right now so that it is clockwise. And the best way to change the orientation, so here's the circle, right? Counterclockwise is like this, right? So circle the radius 2. If you want to go clockwise instead of counterclockwise, then when t starts out at 0, we want the y variable to go in the negative direction first. So that would be this way, right? Turn these arrows around. This would be the orientation that we would need to use, clockwise orientation. So a minus sign right there is one way to handle that. Okay.